Once again, welcome to a new problem. This time we have a cube that sits on a table. We have a cube like that that sits on a flat table, and it happens to have, from a side view. So assume you're looking at the cube like that. Obviously, it has a specific height, L. But just to see the side of the cube in two dimensions, we know it sits on a table, and the cube itself happens to be pulled by a force that's a distance h from the ground level. Okay, it's a distance h from the ground level. So this is L and this is L. The block itself has a weight which we're going to call mg, and it's facing two things. The first one is the fact that it's being pulled by a force F, and there is also a frictional force which we're calling Fr, but remember friction is defined as mu s mg, or sometimes you could define friction as mu s Fn, excuse me, where Fn is the normal reaction. Fn is the normal reaction, and it's some. So there's a force pushing upwards right here, which we're calling Fn. And since Fn is the normal force which acts against the weight based on action and reaction forces, your frictional force will become mu s mg. Remember, mu s is the coefficient of friction, and that's one of the things we want to find. In the first part of the problem, part A, we want to find the static friction. We want to find the static friction or coefficient of static friction when the block begins to slide. And then the second part of the problem, we're assuming that the block will begin to tip. So meaning, it's going to tip at this point. Since the force is moving that way, it means if it tips, it's tipping clockwise, in a clockwise direction. So we want to compute the coefficient of static friction for these two cases. For this block, we do have a weight, and also we do have the force pulling the block itself. The system is in equilibrium, so the sum of forces in the x is 0 because it's moving in the horizontal. And we assume that in terms of the motion, positive x is in the right, and then positive y is in the upwards. So F minus the friction is going to be 0 frictional force, because the F force is in the positive direction and the friction is in the negative direction. So that means the force that's pulling is equivalent to the friction, or we can simplify it by saying it's mu s mg. And since the system is in equilibrium, if we take any torque around any specific point, so the sum of torque around A will be 0. The force is moving towards the right, so the torque that it produces, A, is negative because that's clockwise, and then the weight is pulling downwards, so the torque it produces on A will be positive because it's counterclockwise. So those two torques oppose each other. And just as an addition, the weight is in the middle of the box, so the distance from the edge is L over 2, and that can help us compute the torque. That's the perpendicular distance. So we're going to say positive mg times L over 2, and then minus F times h is going to be 0. Our goal, obviously, is to solve for a coefficient of static friction when it starts to move. And so on the next page, we are assuming that since, just going back to clarify, since F is mu s mg, and we'll also have mg L over 2 minus F, which is mu s mg times h is going to equal 0. Our goal is to solve for mu s, which is the coefficient of static friction. So mu s mgh equals to mg L over 2. The weights cancel out algebraically, and then we can divide both sides by the height where the force is acting, this h right there. And so the coefficient of static friction simplified becomes equal to L over 2h. But that's just part of the problem. So in part A, they wanted us to determine, if the block just begins to slip, then the coefficient of static friction has to be less than L over 2h. And then in part B, if it just begins to tip, then the coefficient of static friction has to be greater than L over 2h. So hope you enjoyed the problem. Feel free to send any questions and comments. Again, this was a problem about solving the coefficient of static friction, and the assumption was that there are two forces, there are actually three forces acting in the system. We do have the force that's pulling the box, and then we also have the weight itself that helps to determine the normal force that's acting upwards. And we also have the frictional force, which is a factor of the static friction. According to equilibrium, the forces in the x are 0, so F minus the frictional force is 0. That helps us to solve for that force in terms of the weight. And then also we take the torque around A, there is equilibrium, so the torque produced by the force which is pulling is equivalent to the torque produced by the weight. And so we go ahead in the next page to make those two equal, as you can see, and then solve for coefficient of static friction. So I hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.